In first topic, we explored how natural systems are monitored and how we uncover the reasons behind the changes we observe. Now we take that understanding one decisive step further. We focus on how resources should be used, how operations should be planned, and how truly sustainable decisions are made. Today, every sector, from mining to energy, from water management to land use planning, is undergoing a profound transformation. Rising demand, climate pressures, and economic imperatives make finding the right balance more critical than ever before. This is where GIS plays a pivotal role. By spatially revealing where resources are located, where operations can be optimized, and where environmental and social risks must be mitigated, GIS directly guides and defends decision-making. In Topic 2, we will examine exactly how GIS is used to plan, allocate, and manage natural resources sustainably, turning insight into concrete, actionable, and regenerative outcomes. In this topic, we focus on how GIS supports sustainable natural resource management from end to end. First, participants will understand how GIS connects the full workflow, monitoring change, planning for the future, and executing operations in the field. We'll look at why planning is essential for balancing environmental, economic, and social priorities, especially under today's climate and resource pressures. We'll also explore how spatial analysis helps identify where resources should be protected, optimized, or restored. Another key focus is how operational tools, such as real-time dashboards, mobile GIS, and digital twins, strengthen field execution and resilience. Finally, we will examine how these principles apply across different sectors: mining, energy systems, pipeline delivery, renewable energy, and agriculture. By the end of this topic, participants will be able to turn monitoring insights into practical, sustainable, and responsible decisions. Sustainability balance. Achieving long-term sustainability requires balancing environmental protection, economic viability, and social well-being without advancing one at the expense of the others. Spatial evidence for decision-making. Using location-based data, imagery, and analytics to guide decisions grounded in real conditions rather than assumptions. Plan-Act workflow. Transforming insight into action by moving from understanding patterns to implementing strategies in the field. Operational resilience. Building systems that can adjust quickly to climate, market, or environmental pressures through continuous feedback. Responsible resource allocation. Directing activities to the most suitable areas while minimizing long-term environmental and operational risk. Integrated sector approach. Applying the same GIS-driven workflow across multiple sectors to ensure consistent, sustainable outcomes. In the previous topic, we focused on the first two steps of the GIS workflow: visualize and understand. We looked at how maps, satellite imagery, field data, and spatial analysis help us see what is changing and why it is changing across agriculture, forests, watersheds, and ecosystems. That foundation allowed us to move from raw observation to meaningful insight. Now, in Topic 2, we move forward in the workflow, into plan and act. This is where GIS shifts from analysis to real decision-making. Demand for food, timber, minerals, water, and clean energy is rising faster than at any point in history. At the same time, climate change, biodiversity loss, and community expectations are shrinking the acceptable space in which industries can operate. When no planning is in place, the default path becomes clear: maximize extraction in the short term. And while this may deliver quick gains, it destroys long-term value, degrading soil, forests, water systems, and the very resources economies depend on. That is why planning is the most critical stage of natural resource management. In Topic 1, we explored what is changing and why. Now we move from understanding to strategy. GIS allows us to test alternative scenarios, evaluate risk-benefit trade-offs, and determine where resources should be protected, optimized, or restored. The planning stage is where actionable, sustainable resource strategies are formed, grounded in spatial evidence rather than assumptions. Planning sets the strategy, but the real impact happens in the field. The act phase is where GIS leaves analysis and becomes a direct operational tool. Mobile GIS and real-time dashboards ensure instant execution and monitoring of field operations. Automated workflows guarantee that processes are fully traceable. The critical factor here is resilience. Action is the stage where we test how the plan performs under stress. Real-time data shows how well operations can adapt to changing conditions, making all systems more flexible against environmental and market pressures. This phase closes the loop. New data from executed actions continuously feeds the system, making it self-improving. Action is where sustainable and resilient management begins. Now that we have covered why planning matters and why action completes the cycle, it's time to look at how these concepts come to life across different sectors. Mining, energy distribution, water systems, and renewable development all rely on operational decisions that must be accurate, transparent, and grounded in sustainability principles. GIS becomes the bridge between strategy and field execution, allowing organizations to monitor compliance, optimize routes, evaluate environmental impacts, and adjust operations in real time. Each sector applies the GIS workflow differently, but the common objective is consistent: reduce risk, improve efficiency, and ensure responsible use of natural resources. In the next section, we'll explore how GIS supports smarter mining operations, energy transition planning, infrastructure delivery, and the expansion of renewable energy. Effective mining strategy begins with seeing the right information in the right context. This is exactly where GIS becomes essential. Geological layers, land use constraints, permitting boundaries, protected areas, infrastructure networks, and regulatory zones all come together in a single spatial environment. With this unified picture, we don't just identify where resources exist, we identify where operations are truly feasible, safe, and sustainable. Early exploration decisions are costly and uncertain. Integrating field observations, geochemical samples, remote sensing, and drone imagery early in the process significantly reduces that uncertainty. GIS guides us toward the right strategy from the very beginning. Which areas offer real potential? Which zones are limited by environmental sensitivities? Which infrastructure options minimize cost and disturbance? In short, the plan phase doesn't simply answer the question, where can we mine? It also answers, where should we mine? And just as importantly, where should we avoid? This makes mining not only more economical, but far more environmentally responsible. The strategy we build during the planning phase becomes meaningful only when it is executed in the field. In this stage, GIS essentially becomes the digital twin of the mine. We can track where equipment is operating, evaluate road conditions, monitor stockpile volumes, and observe environmental indicators, all in real time. From blasting operations to haul road maintenance, many critical activities become safer and more controlled through GIS. Drill hole locations, blast outcomes, and ground deformation are captured digitally, increasing engineering precision. At the same time, EHS teams no longer rely on paper forms. Mobile GIS applications allow fast, transparent, and fully traceable inspections. Most importantly, environmental responsibility becomes part of the daily workflow rather than something reported at the end of the month. Tailings monitoring, water quality, spill detection, and reclamation progress are all continuously tracked. This ensures regulatory compliance while minimizing environmental impact. The act phase is where sustainable mining becomes visible, because every action is measured, monitored, and fed back into the system. This creates a cycle of continuous improvement across the entire operation. In the planning phase, GIS enables energy organizations to bring geology, infrastructure, regulations, environmental constraints, and community considerations together in one unified spatial view. This allows teams to evaluate exploration areas, design safer and more efficient pipeline and facility layouts, and anticipate risks before operations begin. Decarbonization strategies, such as carbon capture and storage, methane reduction, and renewable integration, also depend on accurate spatial analysis. At the same time, health, safety, and environmental considerations must be accounted for early. Safety buffer zones, sensitive habitats, climate-related risks, and regulatory protections all shape where and how energy development can occur. By combining all these factors, GIS helps build long-term, resilient, and responsible energy systems. Once planning is complete, the real value emerges when operations take place in the field. This is where GIS becomes the operational intelligence system of the entire energy network. With real-time asset tracking, organizations can continuously monitor wells, pipelines, substations, vehicles, and field crews, ensuring safe and efficient operations. Operational digital twins bring together live sensor data and engineering models, allowing teams to understand system performance, detect anomalies, and respond proactively. From upstream to midstream activities, fleet routing and transport monitoring ensure materials move safely and on schedule. In downstream operations, GIS enhances refinery efficiency, distribution visibility, and retail supply management. A critical component of execution is the continuous monitoring of health, safety, and environmental conditions. Air quality, spill risks, noise levels, and emergency readiness can be observed and responded to in real time. Through this loop of continuous feedback, field operations become safer, faster, and more resilient, turning strategy into sustainable, responsible action. Delivering natural gas, crude oil, and refined products safely and cost-effectively begins with strong planning. GIS allows pipeline operators to analyze terrain, land use, environmental restrictions, and construction costs to determine the most efficient transmission routes. Digital as-built ensure that construction records remain accurate, compliant, and accessible across teams. With enterprise asset management systems, operators maintain a digital twin of the entire pipeline network, creating a trusted, authoritative source of information for design, permitting, and future upgrades. Integrity planning is also essential. GIS helps identify high-risk segments, pressure zones, and areas where failures could have major consequences. Effective planning builds the foundation for safe, reliable, and sustainable energy delivery. In the operational phase, GIS becomes the intelligence layer of pipeline delivery. Field teams use GIS-enabled mobile apps to perform inspections, complete work orders, report hazards, and track the location of employees in real time, greatly improving worker safety and coordination. Operational dashboards integrate live sensor data, UAV imagery, and pressure or flow measurements to continuously assess pipeline health. Logistics teams rely on smart routing and ICE data to monitor transport and prevent disruptions. When an incident does occur, GIS supports rapid leak detection, spill assessment, emergency alerts, and community notifications. With continuous monitoring of health, safety, and environmental conditions, pipeline operators can act quickly, reduce risks, and ensure that energy moves safely from origin to destination. In renewable energy planning, GIS brings together all relevant information: wind speeds, solar radiation, geothermal zones, and emerging hydrogen infrastructure, to help us clearly understand where each resource can perform best. By evaluating environmental constraints, land use restrictions, permitting requirements, and proximity to transmission networks, GIS enables us to identify not only where projects can be built, but where they should be built for maximum efficiency and minimum impact. This unified view supports more accurate energy yield modeling and helps compare alternative layouts before any investment is made. Cloud-based services make it easy for teams to collaborate, access reliable datasets, and scale analyses across the organization. In short, strong GIS-driven planning ensures that renewable energy projects begin with a solid, sustainable, and long-term strategy. Once renewable energy projects move into the operational phase, GIS becomes the real-time intelligence system that helps teams monitor and manage performance. Dashboards bring together live data from turbines, solar panels, geothermal wells, and hydrogen systems, allowing operators to quickly spot efficiency changes or early signs of technical issues. Mobile GIS and IoT sensors streamline field inspections, maintenance tasks, and safety checks, ensuring that all activities are traceable and responsive. Real-time alerts help protect workers and support rapid intervention when conditions change. GIS also automates compliance and sustainability monitoring, tracking noise, air quality, emissions, and environmental impacts directly within operational workflows. With continuous feedback and clear visibility, renewable energy operations become safer, more efficient, and more resilient over time. In agricultural planning, GIS provides a unified view of soils, land cover, climate patterns, water availability, and crop suitability. By integrating satellite imagery, historical production data, and environmental constraints, GIS helps us evaluate which crops can thrive in which areas and what long-term impacts certain practices may have. This phase also involves identifying risks, such as drought zones, erosion-prone areas, pest pressure regions, and water-stressed basins, so that farmers and agencies can make proactive decisions. Suitability models, yield forecasting, and land use assessments allow organizations to explore multiple scenarios before committing to a strategy. Ultimately, GIS-driven planning ensures that agricultural development becomes both productive and sustainable, using resources efficiently, protecting natural systems, and supporting long-term food security. In the operational phase, GIS supports precision agriculture by integrating real-time data from sensors, field crews, drones, and smart machinery. Operators can monitor crop health, soil moisture, nutrient levels, and weather conditions directly on dynamic dashboards, enabling quicker responses and more accurate interventions. Mobile GIS applications allow fieldworkers to map issues such as disease outbreaks, irrigation failures, or soil anomalies on site, ensuring rapid action. IoT-based monitoring and automated workflows help optimize irrigation schedules, fertilizer application, and harvest timing, reducing waste and improving productivity. The ability to track environmental conditions, water use, runoff, greenhouse gas emissions, and soil degradation also ensures that agricultural practices remain responsible and compliant with sustainability standards. With continuous feedback loops, operations become more efficient, resilient, and aligned with long-term agricultural goals. As we wrap up this topic, it becomes clear that sustainable natural resource management is no longer just about knowing what is happening in our environment. It's about using that knowledge to make smarter, more responsible decisions. GIS gives us the ability to connect all the pieces, from monitoring change, to planning long-term strategies, to executing operations safely and efficiently in the field. We've seen how planning lets us balance environmental protection, economic needs, and community expectations. And we've seen how real-time operational tools, mobile GIS, dashboards, sensors, and digital twins turn those plans into action and help organizations stay resilient in the face of constant change. Across every sector we explored, mining, energy systems, pipeline delivery, renewable power, and agriculture, the goal remains the same: reduce risk, protect resources, and build systems that can endure. Ultimately, sustainability becomes achievable when spatial insight turns into practical, measurable action.